is a statement in Israel, he's from the Hebrew University, and there is a statement saying if you are let's say in the Hebrew University and you don't know somebody, it means that he must be a Russian spy. So now maybe it's not a Russian spy, maybe Iranian spy, but one of those.
It's recorded, please, don't...
It's recorded. Okay, but Etam will tell us some more on algorithmic aspect of fairness, and please enjoy.
For the last time we get to see him.
Thank you very much.
Sure.
Excited to be here, excited to give this talk after Omer and Inbal's talk yesterday. It will be kind of a continuation, repetition, and I don't know, maybe contradiction to the talks yesterday. So I saw this picture in Omer's presentation, and that's a very good example to begin with. About 10 years ago, ProPublica published this nice article titled Machine Bias. There is software used across the country to predict future criminals, and it's based against blacks. And in their investigation, what they showed is that there is this algorithm compass that is used by judges to help in bail decisions. And the idea is that the algorithm gives some prediction of the probability of recidivism of the defendants, the probability that they will recommit a crime in the next 2 years or so. And they show that the algorithm, the score, is much more likely to give false positive errors to black defendants and more false negative errors to white defendants, which is clearly not fair. And the company that developed Compass, their reply was, what do you want from us? That was not the objective that we were aiming for. We were aiming for calibration, and they were not wrong. The Compass score is approximately calibrated within the groups. And like was mentioned yesterday a few times, the problem is that these two notions are incompatible. This example is good for the two parts of my talk today. By the way, I didn't say it's a joint work with Katrina Liggett, whom you all met on a Monday on a totally different issue. So the first part will be the good news. There actually is a continuous trade-off between those otherwise incompatible notions. And it exhibits a Pareto frontier of fairness, something really nice. And then I'll get to the bad news, that post-processing can easily break fairness guarantees. For example, think about the decision that the judge makes based on the score. Even if the score is fair, the decision that the judge makes is not necessarily so, and that's related to Inbal's talk from yesterday. If we have time, I'll also show you some simple fair post-processing algorithms, so it's not a lost case. So in our setting, we have a label, class, category, whatever. R is the output of our algorithm, and like Omer said yesterday, it can be a decision made by a human. It doesn't have to be a computer. It's a prediction, a score, a decision. It can be binary, it can be continuous, whatever we want. And since we're talking about fairness, and specifically group fairness, we have also another variable, A, that represents a protected attribute or a group of the population. You can think as an example to have in mind, Y can be, for example, sick and healthy. The prediction can be low, medium, or high risk, and the groups young and old, just so you have something in mind. And we'll focus on these two notions of statistical group fairness, separation and sufficiency, which I will define in a minute. So separation requires the following. Among individuals with the same true label, it requires that the predictions should not depend on group membership. What does it mean? That given individuals that are sick, that's their true category, the probability of having a prediction low, for example, given that they are old or young, should be the same. And same, for example, for the probability of giving a high prediction, giving that, for example, that they're healthy, should be the same for old and young individuals. And if you see, these are actually the false negative rates and false positive rates within the different groups. So this notion is also known as error rate parity or equalized odds, and we've already seen that. So that was the notion that ProPublica was aiming for in their article. Just to see an example, we have here a population of young individuals with true labels 0 and 1. The base rate, you can see we have 6 individuals in 0, 6 individuals in 1, so the base rate is 50%. We have old individuals with a base rate of 80%. And consider the following prediction of low, medium, and high risk of the disease. So if now we fix one of the categories, for example, the positive one, the individuals that are sick or will develop the disease, we can see that the distribution of the predictions is the same both in the young and the old individuals. You see 3 to 1, 6, 4, 2. It's the same distribution. And the same happens with the second category. So we're fine. This example indeed satisfies separation. But now I want you to take a 90-degree head tilt, and instead of fixing the category, let's fix the level sets, the predictions. Let's take a look on the individuals that received a low prediction. And among those individuals, we see that within the young group, if you received a low prediction, then you are 4 times more likely to not have the disease than to have it, while in the old ones, it's 50-50. Something similar happens here with the medium prediction. So what we see is that the meaning of the prediction is not the same for the 2 different groups in the population. And we ask if that is fair. And for that, we have the next notion, sufficiency, that asks something similar but different. Among individuals who got the same prediction, now we ask that the likelihood of having a certain label, that should be independent of the group membership. Again, we have the probability of being sick given that we got the low prediction, should be the same for old and young individuals, and the same for medium and the same for high. And one way to achieve that is through calibration. So just a reminder, calibration, we say that the score is calibrated. If among people that received the score, some prediction, the probability of having a positive outcome is exactly the score. So among individuals, for example, with score 0.7, exactly 70% are sick. That is calibration. And if we calibrate our scores, our predictions within the groups, we get exactly the requirement of sufficiency. So if the probability of being sick, given that your prediction is 0.2, is exactly 0.2, regardless of whether you're old or young, you satisfy sufficiency if that holds for the different predictions. And again, let's see an example, a prediction, and you can check that the prediction is indeed well calibrated within the groups. But now we'll do the same trick as before. Okay, so this is sufficient, perfect. Same trick as before, but now we fix the categories, and we see that, well, among the old people, you're twice more likely, among the old individuals with, that are sick, with a positive label, you're twice more likely to get a high prediction, 0.75 than the other predictions, whereas for the young individuals is again 50-50. So if you think about that as error rates, the error rate is not the same. And this tension, when I explain it to people, I take an example from the industry, from the tension that there is between the product and the engineering teams in a company. So separation takes the side of the user. The user owns their own label in some sense. And they are worried. They say, okay, assuming that I'm sick, is my probability of getting a high prediction the same regardless of my age? What would happen if I belong to a different group? Would I get a different prediction? That is what worries the user. Whereas the developer owns the prediction, and they ask themselves, okay, assuming that I predicted a high score, is the individual's probability of really being sick the same regardless of their age? So this tension is what makes these two notions to be incompatible, except for, like we saw yesterday, exact predictions or trivial cases, for example, when the base rates are the same, so we have no real fairness problem. But I also want to show you two other predictions that fall in these different notions. So I think that this explains that these two notions are inherently different. So for example, separation allows for the coin flip prediction. If we just flip a coin, that prediction that is totally independent of everything, right? It's probably useless, but it makes the same error rates for all groups. So it is fair in the eyes of separation. Whereas sufficiency allows for the base optimal prediction. And typically, the base optimal prediction will not satisfy separation. So remember these two special predictions. What we asked in our work is whether we can relax these two notions so they become more compatible with each other. So we're not the first to talk about relaxations of these notions. In fact, there are some, it's called structural relaxations. For example, equal opportunity is a relaxation of separation, a relaxation of equalized odds that requires only to equalize the true positive rate. You're right? And there is also a relaxation of sufficiency that considers only the precision and not the false omission rate. But we were more interested in continuous relaxations. And again, that's not something new. In fact, when we optimize or learn fair representations, we usually have to use some kind of a continuous objective. And there are many different ways to do that. But the thing is that all the different continuous relaxed objectives for sufficiency and separation were focused on one of the notions and not on the other. They didn't ask what happens if that relaxation makes those two notions more compatible. So that is what we try to accomplish in our work. So back to the definition of separation, for example, we ask for strict equality between the conditional probability of the prediction given a label for the two different groups. And we say, okay, instead of asking for strict equality, let's measure the distance, some kind of distance between these two distributions. And what we chose is to use mutual information. If you don't know what mutual information is, it's just a measure of association between random variables. And what we ask here is, conditioned on the true label, how much information does the prediction give us with regards to the group? What you have to know is that the mutual information is 0 if there is independence, like we ask in the original condition of separation, and otherwise it can be some positive value. And we do the same for sufficiency. Instead of requiring strict equality, we measure that divergence between the two distributions. We define the deviation from sufficiency as the conditional mutual information given the prediction between the label and the group. And now, having these two measures, we ask what are the best combinations of the deviations from sufficiency separation that are achievable. So we draw two axes. The one for the deviation from sufficiency, that's the vertical, and the horizontal, the deviation from separation. So better separation is achieved to the left, better sufficiency is achieved to the bottom. And now, for a given setting of data, label, protected groups, what we get is a region in the plane of all the measures of deviation from sufficiency and separation that different predictors can achieve. So you can see here, for example, those three special predictors that we were talking about before. You have the coin flip in the perfect separation. You have the base optimal in the perfect sufficiency. And at the origin, we have the exact prediction, which typically is not achieved, cannot be achieved by any predictor. But the most interesting part here is this boundary, which is monotonic and convex, and it actually exhibits a Pareto frontier of fairness. A predictor that achieves a point on this boundary cannot improve either its deviation from separation or sufficiency. And the nice thing about it being convex is that sometimes a little bit of slack, for example, here we see with respect to sufficiency, can get us a lot closer to separation. And again, when you think about that, when learning fair predictors, when optimizing, even when we're dealing with the more complex stuff like multi-calibration, and we allow for some alpha of slack in the error of calibration there, we can still go a long way to the left to achieve better separation, even with a multi-calibrated predictor. And here you can see an example. This is the compass data. The little star is the compass score. And for example, here in the table, you can see the different measures for this point here that is that I marked with a little arrow. And you can see that that point is a little bit worse in terms of the sufficiency, like expected. It's not as well calibrated as the original compass score, but it actually does much better in terms of equal error rates. And this is another example taken from an algorithm developed by Yav, Bechavod, and Katrina. They presented a way to learn predictions that satisfy separation, equalized odds. And here we plot it with respect to these two, deviation from separation and deviation from sufficiency. Now the interesting thing is that the algorithm did not aim for this trade-off at all. And yet you can see that it gives this beautiful convex curve. And the reason is that the algorithm uses a parameter to control for the level of separation, just like a kind of regularization. And the trade-off there is between separation and accuracy, trade-off that we also mentioned yesterday. But accuracy is, in some sense, correlated with perfect sufficiency. So when we turn that knob, we run along the trade-off curve of separation and sufficiency. And that is really nice because you don't have to aim specifically for that trade-off to get these nice results. Yes?
It's like a general segment, like if you do regularization for, say, coefficient G, do you know you're getting close to calibration, or you need to, or is it just like most likely going to go like this, but there is no formal reason to believe it will work like this every time? So
there is a very similar trade-off between the deviation from sufficiency and the information between the prediction and the true label.
Okay.
And there is also a nice concave curve there. Now, I don't have the plots here, but usually that curve, if you plot it now in the terms of deviation from separation and deviation from sufficiency, you won't get the exact trade-off, but you will get something relatively close. Why? Again, because sufficiency is good for accuracy and separation is not, and we get that. But yes, you're right. This is not a trade-off. This is not a trade-off curve that we showed theoretically that exists. But what I'm trying to say here, I'm trying to give you some lens to look at optimizing and learning fair representations. So again, this was the good news. There is a continuous trade-off actually between those otherwise incompatible notions. We have a Pareto frontier of fairness, and the main takeaway here is that you can optimize for one notion and still improve the other implicitly. You just have to look at the right measures and choose the working point that you want. So I can tell you what is better, separation or sufficiency, but I can tell you that if you're aiming for one of them, you can probably do better with respect to the other, which is really nice. Now, in all the work that I presented now, we talked about the relationships between the label, the group, and the prediction. But when I showed you the achievable region, I said that it depended on the specific setting with the data itself. And you should have asked me, where's the data? Where's the data here in the model? So implicitly, we were assuming that the data is in some way in the center of the model. Everything is a function of X, of the data. We can, the group is encoded in X, the label is encoded in X, well, the representation is a function of X. And we can ask, okay, so specifically, the data encodes all the information that exists between the true label and the protected group. Okay, there is no flow of information that goes directly here between A and Y. It all goes through X. And we can ask, what happens if that is not the case? What happens if there is some connection between the group and the label that the data is not expressive enough to encode, to show? And that can happen for many different reasons. For example, the too common use of fairness through unawareness. It can happen because of privacy concerns. It can happen because sometimes we don't know a priori the group. We collect the data, and only later we found out that we can't really infer the protected group from the data that we got. And most importantly, it can happen in post-processing. Because when we have post-processing, when we have a score, when we have a prediction, and then we take that prediction and make another prediction based on the first one, in some sense, the first prediction becomes our new data. And the first prediction shouldn't have encoded all the information that goes between A and Y, right? We didn't need that for the prediction. So in this case, you see there might be, even if X doesn't encode all the information between the label and the group, R does not. And we can be effectively in a state where, like in this picture. So what happens then? When there is information between the group and the label that is not encoded in our data, there is no more guarantee that the trade-off curve between separation of sufficiency and deviation from sufficiency and deviation from separation is monotonic. In fact, there is even no guarantee that we can achieve perfect sufficiency, like this point here. We know, for example, that when the label has more information about the group than the data itself, then for sure that is impossible. We cannot achieve calibration within groups. We cannot achieve multi-calibration. Everything is lost. And this brings me to the second part, which is the bad news, that post-processing, like we just saw, can easily break fairness guarantees. But I actually want to show you a second work that we have. So I showed you that, yes, when you lose information about the connection between Y and A, you can get to a point where sufficiency is impossible. But I can show you that this can happen also in other cases. In this part, I'll focus on the next setting. Like before, we have a label, we have protected group, and we have a group calibrated score. And we want to make some binary decision based only on that score. Very similar to Inbal's setting yesterday. Think about the compass scores, the predictions of recidivism, and R is the judge's decision eventually. Let's take a look at this example. Here we have a prediction that satisfies sufficiency. It is calibrated within the groups. But if we try to threshold these scores and make it a binary decision, and remember, all we know now about the different individuals is their score. We know nothing else. So if we put the threshold here, and we recalculate the probability of being sick within the new level set that we got, we see that it's not calibrated anymore. So maybe we should put the threshold here between the high level and the medium and low, and we get something even worse. So thresholding, putting the same threshold on the entire population can easily break the condition of sufficiency, and it's not always possible to achieve it with thresholding. Yes?
Wait, I got confused a bit about this. So what would you call, like, because normally when I think about calibration, I think about the risk score. But you didn't really define what do you mean by calibration of a binary decision.
Perfect. So first of all, I'll get to it in a second. And so, by the way, you can see here, right? We can look at that. You're right that this is not exactly binary because we're not saying 1 and 0, but still we're giving some scores here, and those scores are not calibrated. You agree that the scores here are not calibrated, right?
There's a condition on being in a particular, getting a particular value the probability should be the same?
We will define it in a second, but there is something a little bit surprising here. Because we said that the whole idea of separation, of sufficiency, is that the predictions mean what they say. So if all the individuals here really have 75% of being sick, and all the individuals there also have 75% of being sick, so why thresholding breaks that? If the scores really mean that risk, how come thresholding breaks that? And the reason is that sufficiency is like, horse blinds. It looks at specific level sets and doesn't care about the distribution of the other level sets. And that breaks everything. The interesting thing is that with separation, with equalized odds, and we didn't get into demographic parity, that is another notion of fairness. If we already have a score that satisfies one of those notions, then any post-processing will be fine. And for some surprising reason, the exact notion that tells us, okay, now the score really means what it says, that doesn't work. And like Inbal showed yesterday, the same happens if we're dealing with continuous scores, even if we have here the distribution of the base optimal predictions. In this example, no threshold will give us something that will be calibrated. So the first thing that we see is that in order for the binary decision to be fair in the sense of sufficiency, this new decision must depend on the group too. So we cannot forget about the group. If we are given only the group calibrated score, we typically cannot produce a fair binary decision from that. Inbal, for your question, what is sufficiency in the binary case? So in the binary case, we have to look only at two predictions, 1 and 0. And what we ask is the probability of sick given 1 and probability of sick given 0 in the two groups should be the same. That is, you can always relabel the 1 to that number, to the value of that probability, and you'll get something that is calibrated. But it is essentially the same. It is equivalent. Now, these values are known as the positive predicted value and the false omission rate. The positive predicted value is also known as precision. And that's why these conditions specifically for the binary case is known as predictive parity. So that is what we are requiring.
Is it possible to get it in a multi-group when the groups are not disjoint, for many groups that are not disjoint?
Absolutely, yes. Remind me if I don't say it in a minute. So how can we do that? How can we still achieve? So we said, okay, now we needed the decision, we need to depend on the group. Let's say we have that information, we have that extra feature. We are based on a score that satisfies sufficiency, that is calibrated within groups, and now we want to make that binary decision. How can we do that? So the first thing that we did was to characterize, or forget for a second, forget the groups. Think about the labels and the predictions and ask, what are all the different values, the different pairs of positive predicted value and false omission rate that are even feasible for different predictions. So again, we put to access the positive predicted values, the horizontal, the vertical is the false omission rate, and what we get is a nice looking feasible region. Okay, so this region corresponds to all the different predictors that we can construct based on some given well-calibrated score. These corners here correspond exactly to deterministic thresholds on the score. And the parts between those corners, those are soft thresholds. They mean that we give 0 to all the scores below some value, 1 to all the scores above that value, and for that specific score bin, we'll have to randomize. In a specific way, but still we'll have to randomize. That is let's call it artifact of the scores being finite, but otherwise the thresholds, both the hard and the soft thresholds, occur exactly in this part, in the boundary of the feasible set. And now for Omer's question, okay, that's for one group. And when we have more than one group, we have to superimpose how the second group has a different distribution of scores. By the way, maybe it has totally different scores. We allow here for different supports of predictions between the two different groups. We superimpose them, and remember that predictive parity means that we have the same value of PPV and FOR for both groups. So the predictive parity happens exactly at the intersection of these two feasible regions. And if you're looking on more than two groups, just keep intersecting them.
Can I give you one example? I'm a bit confused. So let's say that in one group, in S, everybody has probability half, and in T, everybody has probability 3/4.
It's an excellent example.
Perfect. So what would the, a binary zero, well, here perhaps you put everybody in S as 0 and everybody else as 1.
Exactly.
But,
Exactly. So
but with three groups, I can imagine that would be...
that might be impossible, yes.
Like, yes,
You get an
one
empty-
quarter, 1/2 and 3/4, you can't...
Yeah, so I lied here. The feasible sets actually include two degenerate edges that run from this corner here all the way to 1 and all the way to 0. And those edges correspond to constant predictions on the group. So if you have only one score, you can make only one constant prediction. And then if you have two groups with only one score each, what you have is essentially, let's draw it. So what you actually have is something like this, okay? Where these edges correspond to the constant predictors. And when you have two groups, sometimes there is no intersection between the interior of those feasible regions. So here, for example, the only fair predictors will happen in this part where one group will receive a constant prediction all the time, and the other one, well, it might be randomized. Okay? In the case that you were referring to, you don't have interiors at all, so you'll get only this point here. And if you have three groups with only one score, then typically you won't be able to find.
So how is it consistent with your answer that you can do multi-group?
If you have.
Kind of multi-calibration for...
Not always.
Oh no.
It's not like multi-calibration. It's closer to like equal opportunity type thing if you require both.
Yeah, so I didn't say multi-calibration. I said that the same principle here works for more than two groups. You can continue intersecting. Yes, probably at some point the intersection will be empty. Now, if the scores have full support, if you always have scores between 0 and 1, then you're guaranteed that you will have intersection even between infinitely many groups.
Even when they're arbitrarily intersecting?
Yes. You know what? Yeah, I think so.
If
Yes.
you're allowed to have values between 0 and 1, you can just keep P as is, and then you're multi-calibrated, but you're not doing anything.
I'm not, I didn't understand. your
I'm
answer.
saying if you're allowed arbitrary values between 0 and 1, you don't need to post-process. You can just keep your P. And then if P is calibrated, I think you're satisfied.
No, wait a second. You want a binary decision.
No, this is what I'm saying. If you have a binary
No,
decision.
it's a binary decision. So the answer was if there is the entire range of P's, rather than my example when you have either 1/4 and 3/4. If you have everything, then
If you have everything, I think you can always maybe you can think about an example later where.
I suspect it, but okay, let's do it off.
Okay, if we have two groups, and that is for sure. If we have two groups and there is full support, you will always have intersection between the interiors. That is for sure. Okay.
Let's keep the discussion on the third group later, but please.
Can I get like a little bit of intuition of why would you like calibration of a binary decision? Like an example or something that will...
Okay, that's an excellent question. You can ask, for example, in the compass case, we have a risk score, and eventually we have a binary decision. And it's fair to ask, why do we care about fairness of the decision itself? Maybe the decision should depend only on, societal considerations. We don't want people with a risk higher than X to be outside of jail. The same happens probably in healthcare, right? If you know that you have a well-calibrated score and you say, I don't want to take the risk above a certain value that some individual will develop a disease, that's fine. You just have to take into account that in terms of these notions of fairness, your final decision won't necessarily be fair. When it does matter, for example, is when you're in college admissions. That's one example. There is no risk there, right? Imagine that you have some admission test and that you know that the test is well calibrated. It does good on old and young applicants, okay? But eventually, if the distribution of the scores is different between the old and the young applicants, if you put some threshold and you say, okay, everyone above a certain score gets in, what you did eventually is exactly the cutoff will make it such that the expectation, right, of finishing a degree will be different among the different groups, and that's not necessarily what you want. Okay, so I totally agree that when we're talking about true risk, maybe that's not the consideration. But then I'll ask you something different. If eventually your decision is individual, is personal about the risk, why would you ask for a group calibrated score? Maybe you should ask about individual fairness instead. So, I don't know. That's a question. I don't have an answer for it. So like we said, the decisions that satisfy predictive parity are exactly those that correspond to the intersection. And if you look at this specific example, you'll notice something strange. So remember that the corners correspond exactly to thresholds. And if you see here, the intersection does not contain any of those corners. Okay? So no hard threshold will do here for either of the groups. And you can say, but Etam, don't worry. I mean, the randomized thresholds are fine with me. Perfect. Let's look at this example. Okay? So here we have a point with the hard threshold in one group, that is an internal point in the other one. Now, the interesting thing is that we showed that the optimal decision with respect to any loss that we put on the 0-1 decision eventually is always achieved on the boundary of the intersection. Now imagine that it is achieved here in that point. So again, that point will be a perfect threshold in one of the groups, but in the other one, it won't be even a soft threshold. It will be a totally randomized decision rule on the second group. And that's the only way to make it fair. Here again is an example with the compass data set. What you see here is the Caucasian and non-Caucasian groups. And interestingly, the point that achieves maximum accuracy, I don't know if you can see, but it is very, very close to two corners of the in the boundary. So I don't know if that's by design. It may be so. But interestingly, the optimal decision here that also satisfies sufficiency falls very, very close to a clear threshold for both of the groups, which is great, right? But now if you count these corners, right, this corresponds to the putting a threshold on the first score, on the second, third, fourth, and you'll see that it falls on different scores. So even though we have a decision rule that is a perfect threshold for both of the groups, it falls between different scores for each one of the groups. And again, that raises questions going back to the example that we started from. The company that developed Compass said, well, we are well calibrated within the groups, but then you have to ask, wait a second, you use that prediction to make a binary decision. Is that binary decision fair? No, if it's the same threshold for all. So that is it. We saw some good news that there is a continuous trade-off between separation and sufficiency. You can aim for that threshold. You can aim for that Pareto optimal threshold. But you can also keep aiming for each of the notions separately. Just take into account that you can always do a little bit better with respect to the other one. We saw some bad news that post-processing can break specifically the notion of calibration. And I showed you before those nice feasible regions. We have in the paper a very simple algorithm that just traces the boundary of the intersection and gets to the optimal, to the exact optimal point and returns the optimal fair decision. That's all. Thank you.
Thank you for this clean and nice and methodology-based talk. Questions? We had good discussion in between, but if anyone, yeah, please.
So I think it's an interesting question, what do we want to do? Let's take the college admission example. And let's say we really have P star available. So we really know the base optimal predictor. And we want to accept everybody that has probability 95% to finish or above. But if we do that, then it does mean that the signal of being accepted may be different for, so the bad side of it is that, let's say, people go to internships later, the fact that you were accepted to a particular university may mean something different. On the other hand, if you play with the threshold, I mean, perhaps what the university can afford is to have 1/20% of, it can handle 1/20 students that do badly. So this is kind of an external. The threshold was not chosen to be fair by any kind of notion. It was chosen because that's what the university, that's the loss that they can afford. I mean, and you can imagine an healthcare example where a probability of 1/30 of misdiagnosing or not diagnosing, perhaps we can handle, and that's the main criteria.
So I agree. You're adding another consideration here that is close to what Inbal showed yesterday. Right? If you have some other constraints, then I don't know. That's a good question. If you put a constraint on the number of admissions that you allow, what happens then? But I can. So that's an excellent question. We didn't deal with that. Here we assumed an unconstrained world where we only require to make a fair decision. But I'll take on what you said about the signal now when the graduated student gets hired, then the company will ask, wait a second, the fact that you were admitted doesn't mean the same because you belong to a different group. If you take a point in the intersection, then it means exactly the same on average. But the surprising thing is that in this example, for the yellow group, it will be a clear threshold. But for the blue group, since it's an internal point, the decision rule here will randomize so it will even admit individuals that are totally not suited for studies.
In terms of a signal, the expectation may not be enough. I guess that's what you're saying.
Exactly. In some sense, both separation and sufficiency, calibration, are a first order notion. And maybe it's not enough.
For signal, I would assume it is, but people thinking average.
No, you can think, so a similar, maybe, by the way, maybe it is equivalent or related somehow, but a similar question is, what happens if you have a well-calibrated score that gives the base rate for one group and is very, very precise on the other group? The signal in terms of calibration is the same, but you're missing some information there. So yeah, maybe calibration is not enough.
Or perhaps it's not the right thing for binary decisions.
Or for admissions.
Sorry, I have a very basic question. Can you go back to your definitions of separation and sufficiency?
You have sufficiency, for example.
So when you say who got the same prediction, that's the, so when you say the same prediction, then later you were using low, medium, high as your prediction.
Mm-hmm.
So if I'm assuming that I'm doing binary classification, low, medium, high is actually a score.
1 and 0.
Okay, so the prediction is a discretization of the score as well. Is it the case, even with the discretization of the score, that you know that even this is satisfied for the Bayes optimal model? Does it still depend on the discretization function that goes from the risk to the predicted score?
So the Bayes optimal is usually continuous for
right. So I imagine I have a model that takes X and spits out a continuous probabilistic score,
mm-hmm.
and then I have another function that takes that and returns a 1 or 0.
Oh,
I
yes.
chain those together to get my prediction.
Absolutely. The
Right.
problem here that we consider, you can take S to be the Bayes optimal.
And then sufficiency is not guaranteed.
Absolutely.
Okay, sorry. I thought I misheard something.
No.
Okay, yeah.
Yes, absolutely. And maybe I didn't stress that enough. It is surprising. it is surprising that even if you take such an amazing score, if you have a genie that gives you that score, still nobody can guarantee you that you can make a binary decision. And even if when you can do, so in the unconstrained setting, you know that thresholding is always optimal, right? But here, not only that thresholding is not optimal for one group, the other groups sometimes might get such weird decision rules that then you can also ask, wait a second, is that fair? Well, it is according to this definition, but
Sort of related, but I think I figured out what was weird. Suppose you don't care for being optimal in terms of doing the best binary decision. Then, if I understand correctly, completely randomizing your score would be sufficient. Like, would satisfy sufficiency. It would just be a bad decision.
completely randomizing the
Like,
score.
if your P was 0.5, then accept with probability 0.5. Would that satisfy it? It would be a bad
Oh
decision.
yes, but absolutely. But
saying it would be a good
for each group independently.
Yeah. But it doesn't matter, because if you just use your P, you're doing the same for every group. It will be a bad decision.
No, you need it according to the base rate.
I mean, you're calibrated within groups, so yes.
So for each group, you have your own coin, right? So yes. And by the way, that point that you're referring to is exactly the corner here.
Yeah, like bad decision.
There was another questions here. Yeah, please.
Yeah, I had a question. So when you compared sufficiency and separation and along the Pareto frontier, there's a question like where, right, on the Pareto frontier? That's a really hard question, especially from the standpoint of regulating for fairness. What are your thoughts on where along the frontier one should locate that point?
So
The trade-off.
excellent question. First, I'll answer you for the record. It's not my job. I mean, and I'm happy for that, because really I don't know. My job is to tell practitioners, listen, you have more than two options, okay? So up until now, people think, okay, you have to choose either your values go with separation or with sufficiency. Yes, you can take that caricature of the user and the developer and decide according to that. But maybe yes, maybe you can say, I want to have 80% of one and 20% of the other. Maybe that makes sense. I really don't know. What I do know is what I said before, that in real life, in practice, you never achieve neither perfect separation nor perfect sufficiency. And what I'm saying is that, you know what, don't ask yourself if you want to be on the Pareto curve. I don't know. But even if you're aiming for one of these two notions, then just take a look at these measures and you will see that turning a knob will get you much, much better with respect to the other one. And why not, right?
Okay, I think it's a good point to stop. And thank you very much, Etam. And we'll convene again after a short break. And then we have another two talks.